Right. Ma'aloelelei, ta'alofa lava, tēnā koutou katoa. Greetings and welcome everybody to this special session on the Tonga-Hunga Ha-Apai volcanic eruption and tsunami. Now, this is one of the final sessions of the conference prior to the closing ceremony, so we have assembled an outstanding lineup of speakers for you, representing our entire Australasia and Southwest Pacific region, who have kindly agreed to share their work, knowledge, mahi, and learnings from the event. We hope it'll certainly keep your interest levels peaked throughout this session. A bit of housekeeping before we get underway. Please remember to use the live Q&A tab to ask any questions you may have for each speaker. And please also specify the specific speaker name, who your question might be addressed to. And we ask that because we're probably going to hold off all answering of all questions until perhaps the final 20 or so minutes, where we'll have an open dialogue and engage in further discussions from there. Without further ado, I welcome you all. Thank you for all your participation. I'd like to introduce our first speakers who hail from the Kingdom of Tonga. So Mr. Taniela Kula, our Deputy Permanent Secretary for the Ministry of Lands and Natural Resources in the Kingdom of Tonga, as well as Mr. Ofafa Anunu, the Director of the Tonga Meteorological and Coast Radio Services. And they'll be speaking to us on the Tonga Meteorological Service and Tonga Geoscience Service, the effects and observations of the eruption and tsunami in Tonga. Daniela, if I could request that you share your screen and please turn your mic on, and over to you, mate. Take it away.
Thank you very much, Sean. Let me just start my screen. I think I'm lost in my screen. Here we go. Sorry. Thank you very much, and take the opportunity on behalf of the Tonga Ministry of Lands and Natural Resources. Thank you, Sean, and the organizers for allowing us to present the observation and effects of the eruption and the tsunami on the 15th of January 2020. Get on to my and it's something that Tonga and of course the ministry will won't forget, but we'll continue to learn from it and improve our monitoring of any volcanic eruptions in Tonga and of course associated tsunamis. And on this particular day, a lot of events took place. I was outside in the field and receiving reports from the officers, receiving reports from the beach side, on the western side, and even up to date, we're still collating all the information that's been gathering, that was collected by individual citizens from all over the place, recording the clouds and also recording the waves as they arrived on the western side where it first arrived. The slides that you're seeing now is just a show of the volcano prior to the eruption. Of course, the eruption started on the 20th of December. And also this is a slide on the 24th, which shows that the eruption took place. And it has also shown that the island has increased in size, and also the vent is also coming out from between the events of the 2014 and 2015. You can see more eruption on the 24th, but it has slowed down a little bit just before we came on to the island on the 30th of December. And most of that drone footage that we captured on the 30th of December is online, been used by many medias, but you can see that the eruption has slowed down a little bit on the 24th and leading up to the 30th. And of course, up to the 2nd of December, we noted the large reduction in the eruption. And of course, this is a capture on the 6th, showing ash still emitting from the volcano. And also the 7th, which really slowed down. And eruption was quiet for about a week's time, and also we declared it to have ceased on the 11th, and then suddenly eruption on the 15th just surprised us all, and we did not get this picture until a week after the 16th because of our cutoff from our cable being cut off from our internet. But this picture was revealing that the island was split in half on the eruption of the 14th. And then a few hours after this slide on 5 p.m. local time, and then the famous satellite Himawari 8 that's gone viral around the world on the 15th. So also this famous video that shows the shockwave traveling around the globe 4 times as reported by other medias. So after the eruption, we had a lot of engagement with international experts, and this is a study provided by our Japanese colleagues. And the study actually detects that the eruption started earlier than we initially thought. Immediately after the eruption we had thought that the large eruption started at 4:15 because of the USGS publication on the earthquake catalog. But we now learn that it started earlier than that. And a later observation, or using Himawari meteorological satellite, we actually noted that the eruption actually started much earlier, around 4:43 a.m. UTC time. So as information emerges and more analysis of imageries, we're getting new piece of the puzzle, and the stories change every time. So all the progressive analysis of trying to determine what actually happened. Also the seismograph that you see here from the Fiji seismometer, which is about 700 kilometers away, which also you see here in C, which is very interesting. The yellow line is actually the airwave-induced ground motion. And you also see in this analysis is the pressure data from the Tonga Meteorological Services. And I'm sure Alpha will touch on this later on. But so this slide will be later also discussed by our colleagues that are presenting today. So I won't go too much on this slide. This is a compilation of study by Shane Cronin, and authors will be presenting today. So I won't discuss this too much, but overall, this slide actually means that there were more activities going on at the seafloor that we have to determine, and we can finalize after mapping and sampling of the volcano that's currently undertaken by scientists from Korea and also New Zealand. So I won't talk too much on that. But the interesting part on this one, this also shows that the highest plume on this goes imagery and also the Himawari seems to have emerged from the south side. So this south side of the caldera is assumed to be trapdoor caldera opening. So the initial eruption started from that side. And we assume that the tsunami actually started with that initial eruption. Why I say this? Because the report that came in from the western side, coastal beaches, where actually the reports came in just after 5 p.m. That the waves were funny on the western side, people who were swimming there. And then from correlating the information we gathered, so the initial waves actually arrived around the 5:15, so a short period after the earthquake that were categorized by USGS. So the waves actually arrived much earlier than we anticipated or expected. This is tsunami propagation model, a Japanese colleague, and I just shared it because of the arrival time determined by the propagation model is around 5:20. So that's just a correlation to what to the reports that was given from the western side before we actually understood that the big tsunami coming with the eruption. And you can also see as the wave progressed that Ewa was hit hard by the waves swinging down the south of Tongatapu.
Daniela, my friend, just to pass on the 1.5 minute warning. Thank you, mate.
Okay. So I guess you've seen tide gauge. This is the tide gauge on the Nuku'alofa side, which you can see it's much slower. The first wave recorded here is 4:40:32. This time, the people in the western side already evacuated. So there has to be some setup that will ensure that when the first wave arrives, that we know about it and we have a record of it. This is also our GNS station in Tongatapu. You can see there's some motions, displacement, vertical and horizontal, during the same time when the eruption was going on. So we should consider in the future, the GPS station should be included in for tsunami warning or early warning systems. So these are some of the slides of the impact of this tsunami. This is from Ewa urban area, Honua Center. You can see the waves going in up to 300 meters inland and devastated everything along its path, cemeteries, government offices, police, and the courts in this area. More than 40 families was devastated by up in the Ha-Apai group. You can see the residential area on this northwestern corner of the island. So the waves propagated around to the north and then hit from that side, and also waves coming down from the southwest side, hitting on this side of the island, but wiped up the whole village. This is Nomuka Island, which is around 70 kilometers from northeast from the volcano. It wiped out almost half of the residential area. The waves, as observed by the people here, where we are estimating 7 meters high on the water when it came across another island that was just in front of it and before wiping out all. So the seawall was actually about almost 20 meters in front of this house. I mean the coastal road before the beach. So the beachfront line was receding to almost 50 meters in some locations here. So this slide is just showing the remnants of the Hunga volcano. This is taken by the Tonga Progressive Commission from one of the flights that lifted off from Tonga going to the new islands to observe the status of eruption. And for this is provided by NASA. You can see the overall remnants of the island. You can see the outline of the volcano before the eruption. And of course, after the eruptions, there were earthquakes that kept on hitting us, about 80 earthquakes between Tonga, Tapu, and volcano. They range from 4.4 to 5 magnitudes. And they kept on until the 16th of, so a total month after the initial eruption on the 15th. So this is a timeline that our Japanese colleagues has put together based on the data that they analyzed that we have provided them. So this is a work in progress. Shane Cronin and his group are also working on updating the timelines of these events. And of course, as we receive information, we keep on changing because this is a progressive timeline. So the total effects of the tsunami, it rose up to 15 meters on the western side of the island. Some are just above 12 meters. On the main urban area of Nuku'alofa was up to 3 meters approximately. And it's 15 meters also in the Ewa Island, 12 meters. We estimated for the Ha-Apai group, and some are 8 meters. It also damaged about 600 structures and about 1,500 people displaced. And those are the effects. And right now, we're working on the relocation strategy with the ministry overall, based on the effects and the studies that we're partnering with other agencies. Thank you very much, Sean.
Mahalo Aupito. Thank you very much for that, Daniela. And we really appreciate this fantastic talk you've given, and also for setting the context for the next talks that we have lined up. Now, we have run over slightly over time, so Ofa, I will just already immediately call on you, my friend. If you could, actually, Jess, if I may call on you to kindly share Ofa. And Ofa, just if you could unmute your mic, thank you. Please take it away.
Thank you, Sean, and I appreciate the opportunity to present from the warning perspective. I'll be talking about the event on the 14th and the 15th because of the warnings that we had given out on both days. Next slide, please. Next slide. Yeah, so event number 1 on the 14th of January, this was 1 week after the volcano had kind of settled down and gone silent, as Daniela mentioned. And on that morning, about 7 a.m., Nuku'alofa woke up to a moderate to strong sulfur smell that covered the island. And then at 8 o'clock, there were reports of ash falling on Fonoi Island in Ha-Apai. Also reports from one of our meteorological officers that was on the inter-island ferry approaching Tongatapu that morning of ashfall. At around just after 11, we issued our first tsunami marine warnings. This was based on some erratic tide changes that were reported from Mango Island in Ha-Apai and from the harbor master at Nuku'alofa Wharf, together with sea level readings that we had access to from the gauge at the wharf. And then we issued the 7 tsunami warnings, marine warnings after that, up until the next morning on Saturday, the 15th. Then we canceled all the warnings then. But as we know, at 5 o'clock p.m. on the same day in the afternoon, that's when the major eruptions happened. Next slide. Next slide, please. I just wanted to show this. This was on the 14th. The tide gauge on the 14th up to when we canceled our warnings. This in going back and looking at the data, and it's something that I want to question the scientific community. Although we canceled on that day, it looks and the waves seem to have died down. But if you look at the residual trend, the residual is taking away the tide differences. Although the waves had diminished and gone small, but the actual trend in the residual had been going up. So I don't know if that's some investigation needs to go into there. If there is some signal there that could indicate that a major event was to follow. Next slide. So the timelines on the 15th, when the major eruptions were happened at 5:13, eruption was observed from the Met Office at the airport. Then we called up the Geology Office and reported to them. Some minutes later, at 5:23, a loud blast was heard from the volcano. This blast was very significant and very loud. The pressure drops resulted in you could feel it that your ears were popping. Immediately, when we heard that, urgent tsunami warnings went out on the radio, warning for all the people to evacuate. And then we continued on into the night. Around 6:30 that evening, when the ash started falling, everything went off. The communications went off. So from 6:30 until probably 6 weeks after the event, all communications were down. But that evening, when all communications went down, we had a handover from the geological office for the Met Office to monitor the volcano, because I think we were the only people in the country that were still able to contact outside via a handheld satellite phone. Next slide. And then warnings went on. We downgraded warnings to marine warnings at almost 2 in the morning on Sunday. and then the marine warnings continued, and then we canceled all the warnings at 1 p.m. on Monday. Next slide. Daniela already showed this, but I just wanted to show when the tide gauge failed, and we were operating in the dark from then on. The information that we used to downgrade our warnings was based on a request that we made to Daniela to personally go out to the wharf and basically put a stick in the ocean and observe it for 20 minutes and report back to very primitive methods of assessing the situation. Next slide.
Ofa, apologies to interrupt, my friend. We have 1 more minute left. Back over to you.
Thank you, Sean. This is just the observation we saw from the airport when the big bang happened. Next slide. Next. This is the tsunami arriving in Tongatapu in Nuku'alofa at 5:47. So we were able to warn for Nuku'alofa 20 minutes before the wave arrived, and evacuations took place. It's only small to the western side, and small islands out that we weren't able to warn for because of the vicinity to the volcano. Next slide. This is just the estimated travel times. You can see there the wave first arrived to the western part of Nuku'alofa 8 minutes after the sound, after the eruption. It just goes to see how, to show how quick these things can happen. Next slide. The pressure readings are recorded from when it started to 20 minutes later. This is from our meteorological stations. Within 20 minutes, the pressure dropped from being where it was by almost 10 millibars. So meteorologically speaking, it went from fine weather to a category 2 cyclone in 20 minutes. Next slide. We also observed almost 50 knot wind gusts at the meteorological station at the airport. Next slide. Next slide, please. You can continue. Next slide. Next. I probably won't go in too much into the effects, but the main things were the communications being cut, and our only communications was through satellite phone to the Volcanic Ash Advisory Center to Wellington. Next slide. That's the conditions that took place that evening. We had to. That's the little handheld that Tonga was using to communicate to the rest of the world, basically, on the condition of the observation of the volcano. Next slide. The impacts. I'm not going to go into it too detail, but 4 deaths right now. Government is reconstructing over 200 homes. Next slide. That's one of the resorts to the west, totally destroyed. Next slide. agriculture was affected, especially the fruit trees and vegetables. Next slide. In this, my last slide, on the lessons learned. Mainly, I want to just talk about the importance of the awareness on natural science to the communities for when these quick onset events happen. Before the eruptions, we had the Met Service had gone out to all communities conducting tsunami awareness, all communities throughout the country. It was over 30 islands and on the main island. So, and that was our main message was for the public was to move when the early warning natural signs are cited, and I think that's we can work on developing a better scientific tsunami warnings, but that is the main message that we put out, and we think that that is the correct way of doing things, and I think that is what saved a lot of lives from this event. But, thank you, Sean, for the opportunity.
Ma loa upito ofa. Thank you very much for that fascinating talk. And again, once again, I thank both you and Daniela for sharing your time, for being here with us. We will move directly on to the next round of speakers, given that we are running a little bit behind time. Thank you once again, Ofa and Daniela. I would like at this stage to introduce our next speakers, Professor Siautu Alefaio, who will be accompanied by Susanna Vaifo'o, who is an executive assistant at Affirming Works based in Taumaki Makaurau, and Siautu is based in Te Whanganui-a-Tara, Wellington, and they'll be sharing their mahi and speaking to us on the longer term response and how the Tongan diaspora in New Zealand contributed to recovery efforts. Siautu, please, if I can request you share your screen and unmute your speaker. Marlo, over to you.
Mahalo everyone, talofa lava. I'll hand it over to Susanna Vaifo'o from Affirming Works just to open us up while I open our PowerPoint. Please, Summer.
Malo brito Sean and Siatu. Go gole pe ke ho whanga hi ngahi lea na e kamata aki ai konwhele nisi ko e ni. Ka tāpe mo oko e whainga mali ko e ni ke whai halawe ke ka weinga. Ki mua pe a whai matala noa ku matu whetuku pe a whainga mali ko e ni ke whakamalo atu ke koe Sean me ka ngawe hono ko toa pe I he ma o whainga mali e pe a kumawhia ma o ke whakamalo atu ke koe Ofa mo Daniela koe uhi koe ngawe lahi o kumo whai me i tonga na. Te awe whainga mali ko e ni ke a Siatu ke ne ka mata e matala noa I he hoatani. I'll just pass it back to Siatu, but just in summary, we just wanted to acknowledge the organizers of this conference, Sean and the wonderful team, as well as Ofa and Daniela for all their work in Tonga. Malo Siatu.
Well, thank you so much, Summer. We'll try and make up the time for you there, Sean, and be really brief. But just to, as Sana said, to acknowledge our amazing leaders in Tonga. I myself am not Tongan, I am Samoan, but we have worked across with Ofa and Tonga with the community. You may be wondering why a psychologist and youth worker and community people are here in the hard geosciences spaces. But I was invited, we've been doing work across in Tonga in the disaster resilience space for some time, and when the Tonga-Hunga volcano erupted, I was invited to a T-Surge meeting here in Aotearoa, New Zealand. I wondered why I would go ahead right now, given that generally psychosocial recovery comes a long time after. But actually sitting in that meeting and listening to the awesome information that you all are privileged to hear every day is something that the general public and myself often don't get access to. And one of the things I often do is think about all the information that is being shared at warp speed what information would be really useful for communities in crisis to understand in the immediate phase. And so when I was listening on the T-Surge meeting, one of the questions I had asked them was, so all of this amazing and good information, I'm really grateful for the work they're doing. What information would be really useful for the community who's responding from here in Aotearoa, New Zealand to know right now? So for me, it was thinking about the Tongan community, the diaspora. We use that term to describe a lot of our Pacific nations, people who have dispersed out of their island nations and are living here in Aotearoa, New Zealand. So at that time, the Tongan diaspora were already responding. And often it's the diaspora that sustains the communities that are in disaster long after. So one of the things that happened for us was listening to all of the amazing geoscience information and thinking, is any of this information useful right now in the immediate stage? And that's when I think it was Emily, Sean, and the team and T-Surge were started to be, oh yes, da da da. Let's look at the translation. It hadn't been done before. It had been done overseas, I think in Peru, but it hadn't been done here in the Pacific. So basically what we enacted is what I call a NIU. NIU is in baby coconut. It's a Samoan word for baby coconut, but it's also the acronym that we use for our research collective, which is Navigate in Unity. And so for us, it's about this navigating in unity through the coconut wireless, ways in which someone who knows someone who knows someone. And from there, we had the Tongan community come together to Emeline, who's the director of Affirming Works, and her team. They went to work here in Aotearoa, New Zealand, looking at translating some of the key messages for Ashfall. And these messages, because Lord Whakawhenua was here, as I understand, as the Speaker of the House in Tonga was here, he was able to do a quick turnaround in information openings, I guess, for want of a better word, when oftentimes government to government can be stored. Sometimes the coconut wireless gets things across faster. So I'll hand it over now to Sana to talk about how then when these were translated, these were then shipped in their food parcels and boxes that the team at Affirming Works enacted, and how that's had an impact over in Tonga with their families there. Thank you, Sana.
Thank you, Siatu. So Tag Tonga is a community-led aid initiative set up by Affirming Works with staff on the ground. It was first established in 2018 after Cyclone Gita in 2020, and then in 2020 with Cyclone Herald. So it made sense to reactivate this initiative following the eruption and the tsunami this year. So in January, shortly after the disaster hit, we felt especially vulnerable because we weren't able to have any communication with our staff, with our families, of anyone in Tonga, as stated by Offa. So we were just listening to the radio and playing it ear by ear, but the directors of Affirming Works felt quite strongly to reactivate the Tag Tonga initiative. So we did that a few days after in partnership with Siatu and the team from New Patch. So I'd just like to acknowledge the Affirming Works executive directors, Alipate and Emeline Mafileo, for their work that made Tag Tonga possible. So it was just a few days after we also set up the Give a Little page for donors to donate people were wanting to donate, they were wanting to support the cause, they were wanting to contribute to the recovery of Tonga, and for Affirming Works, that was through packing 900 food parcels and shipping that to Tonga for people in need in a 40-foot container. These had your essential items like Pacific foods and also like things like mask and hand sanitizer. And the one page that Siatu just shared, which was in Tongan and English, it had key details that were given to us by Siatu and the team from the geoscientists. So it really identified what these key messages that people were needing to know, and just clarifying it to them through simple, very important messaging. So our staff in Tonga on the ground have received these 900 food parcels. They have all been distributed to families in need. As you can see, there has already been another shipment to Tonga. As a result, we can see that in Patangata, our staff have delivered to over 138 food parcels to these families who have had to relocate or live in tents, and they've been working closely with Tongan officers, with the Tongan office in Tonga, to identify these families. And our staff report on this to us weekly, and it was just to affirm the importance of these food parcels. We also, they also told us about how it went hand in hand with the Omicron outbreak. So the food parcels were quite timely for them, as well as in Tonga, families only had like 1 day to shop when it was when they were under lockdown. So it was a response to the disaster, but it also played a key part in keeping our families safe when it came to the Omicron outbreak as well. So just to wrap things up from my end, our team have been able to deliver all 900 food parcels sent in the fresh shipment, with initial deliveries to all those that were affected the most. So areas like Patangata, Kanokupolo, and Siasia Island, to name a few. Staff work closely with key people in Tonga that have made it possible to do these deliveries. And we also have a registration for all these people as well. So we can see that most of our food parcels, this was for the end of March, were due to people needing food support because they were displaced due to the volcano eruption. Thank you, Seattle.
Thank you, Sana. And so that's really us, Sean. It's really about how we can come together across different disciplines and bring to life, I guess, the good information that all you amazing geoscientists come to work to do, and make it edible for everyday people who are dealing with crisis. So, whafte lava, Sean, and malo opito again to Ofa, the Director of MET, and also Daniela. Thank you once again for having us on your panel, Sean.
Mahalo au pito whaftai tele lava si autu and Sana, and thank you very much. We really appreciate you being here with us. I suppose, for lack of a better description, us crazy scientists. So thank you very much for taking time out of your busy schedule to share that mahi and all that knowledge with us. I would like to just remind our audience that if anyone has any questions, please feel free to use our live Q&A. But without further ado, we will keep the ball rolling. So I would like to introduce Professor James White from the University of Otago, based in Otepoti, Dunedin. James will be speaking to us on a geological overview of the Tonga-Hunga Ha-Apai volcanic eruption. James, over to you, please, mate. Please take it away.
Thanks, Sean. Kia ora all. I'm going to be just hitting a few of the high points of the eruption and leave you with some interesting things I think at least are interesting to us volcanologists to think about. And this is definitely not just my work. You can see here that there's a wide, large cast involved, led by Shane Cronin, but with lots of others. And one of the things that's really fascinating to us is that this eruption started off pretty ordinary, and then it went rogue. Something really different happened. So this is the context. We have here the 2014-2015 cone that had been added to already by the beginning of the 2022 eruption, but it was largely filling in this black area up at the top. We had some earlier eruptions in 2009, 1988, so this is quite an active sort of a volcano. And you can also see that the volcano is surrounded by these various areas, collapse chutes, where things have flowed down the sides of the volcano at previous times. Daniela has already shown us some of these, so I'm just going to hit a couple of them. So before this last eruption series, we were looking at the Tonga-Hunga Ha-Apai islands put together with this 2014-2015 cone. Later on, we had built a second cone during the 2022 eruption, which started in December. And this is a really important image, which shows that we've lost a big chunk of the volcano just before the climactic eruption. It's relatively shallow at the south, and it looks deeper at the north with no waves breaking. So it looks like associated with that earlier part of the eruption on the 14th, that we may have lost part of the volcano off up to the north. And this is more or less what's left now. A lot of water with some very small islands, nothing left of the southern reefs. And there's only about 25% remaining now of Ha-Apai, and an even smaller proportion, about 9% of the Tonga-Hunga. What seems to be present here now is a deep hole that is from fish finder sonar that was reported by Shane Cronin, something over 1/4 of a kilometer deep. One of the other key observations coming out of helicopter flights and summarized here by images from Shane Cronin and annotated by Marco Brenna. They've been working on the islands in 2014, 2015, and we're fascinated to see the changes that had taken place afterwards. So we saw that the islands had gotten a lot smaller in area already. They also lost a lot of height. They lost all of the deposits that had been present and formed in 2014, 2015, all the ones from 2009, and in fact, everything back to about 1,000 years ago. All of that record is now stripped away from the islands, whether that's from large airwaves or more plausibly from intense pyroclastic density currents or from water waves splashing over the island isn't yet known. But what's clear is that we've lost a lot of material off the top, as well as stuff sliding off in different directions, either outward from the volcano or inward into the opened caldera. The eruption proceeded in some phases. Virtually all of the main part of the eruption took place in the first hour or so. This is the areas of lightning intensity within the cloud. And so you can see this is latitude in degrees, so it's covering quite a broad area. It widened out very rapidly as that umbrella cloud started spreading. And as it got above about 8 kilometers, the plume starts generating lightning. And this was the most lightning rich event ever produced, as far as I understand. This information is from Alexa Van Eaton at USGS and her colleagues. And then the eruption sort of then waned and continued for a while, but virtually all of the widespread deposits and most of the intense activity we think took place in this first hour. Again, the onset, Taniela was giving us information about sort of the changing information we're getting from different sources about exactly when the eruption began. But what's pretty clear is that the onset, this eruption wasn't tremendously different from what had been happening in December. And then we had a big acceleration around 4:15. We're looking at very high order amounts of material being ejected from the volcano, largest for decades, larger than Pinatubo by an order of magnitudes. That was the big volcano in 1991 in the Philippines. And so this was the big event. It was associated with those loud sounds that people could hear and many additional sounds. A lot of the information we've been considering about the volcano, particularly in terms of its magnitude, comes from looking at satellite imagery of those volcanic plumes and then applying models that have been developed through time. This one is from ASH 3D, again from Alexa Van Eaton and her colleagues at USGS. It's for about a 1 cubic kilometer of ash going into the plume, and it gives us around 3 centimeters of ash in Nuku'alofa, which is probably about what we're seeing. And it's got a distribution that we're still trying to put together, but it's a bit difficult because we'd like to have basically a bunch of islands headed out this way and some crosswind winds to give us full information, and those simply don't exist, nor have we been able to find ships in the right place at the right time. My own specific interest is in the particles that have come out of this eruption, and we see a range of different shapes. And we also see that there's quite a lot that have really intense fracturing, and it's this particular type of fracture that we see here in an SEM image that interests us most. because that's a really high rate, intense kind of fragmentation that's commonly associated with magma water explosions, which we think took place at this volcano. But there's also a range of others. So these stretched out ones are telling you that the magma was being pulled apart in a fluid way as it was coming out. We see lots of conchoidal and stepped fractures, again, indications of intense breakup of the magma. And we also have some interesting information that I'm sure others will talk more about submarine cables. So the domestic cable was cut earlier, and when people went back to repair it, they found that about 100 kilometers of it had been buried, so it's not repaired yet. The other cable, quite interestingly, was broken here, and it was actually the end tip of it was displaced 5 kilometers toward the volcano, and maybe that Emily will talk more about this later. So some sort of submarine currents were required to both bury the domestic cable and to break the international cable. And at least some of those currents had to be moving northward to cause that displacement. So now let's just sort of summarize this, and hopefully I won't run over my time. So the eruption began ordinary, and then something happened that changed everything. This was that big acceleration. It's almost certainly associated in some way with that Big Bang that was so widely heard. The ash fragment internal textures, which I didn't really show you, but they look really ordinary. They look very much like what was going on in 2014, 2015. They're not telling us something that we would usually see in an eruption about why there was a sudden change in eruption intensity. The ash fragment shapes, however, do strongly suggest explosive magma-water interaction. So this is the way that the magma is fragmented. It doesn't directly tell us why it's suddenly coming up so rapidly, though. So those are two separate questions, and there's really still quite a mystery about this first one. The caldera area is now a big hole, so it's basically a rock-lined cup that goes down a 1/4 kilometer or so. We're pretty sure there were outward landslides, starting with that removal of the volcano that had been built off to the north before the main eruption. The big explosions were probably taking place inside that central part of the volcano, so in the caldera area. And again, we can think of that as an area that's filled with water, but it has a rock rim around it. So we may not be seeing a direct signature of those in waves that are running out over large distances. The volcanic plume is really water rich and ash poor, so there's lots of vaporized seawater. This was probably partly a result of, or maybe perhaps largely a result of this interaction of magma with water. And one of the other things we can see evidence for that in the particles is that some of them are actually stuck together with precipitated salts. So that's a signature of the seawater. The plume didn't initiate from a strong vertical jet. So this is really important observations from Alexa Van Eaton and her colleagues in particular, but also from the Japanese group. This plume was fed over a fairly large area. And that is probably an indication of this sort of breakup of the caldera with many different parts probably erupting at the same time. And potentially also some of this plume is being fed from density currents that are moving out laterally away from the volcano along the surface of the sea. And here's the big one for thinking about other coasts. The models for the total amount of ash coming out of this are estimating on the order of maybe 5 to 6 kilometers, but only a kilometer that seems to be represented by the fall deposits we've seen so far. There's new information that is coming from people looking at the seafloor off to the west, but I don't really have much to say about that yet. Shane Cronin and his colleagues will be talking more about that in the future, I'm sure. But the key message here is that we have multiple cubic kilometers of material that seem to have disappeared into the water near the volcano during the eruption. And I'm guessing that probably made some waves. And I'll stop with that. Thank you.
Mahalo Aupito, James. Thank you very much for that very interesting talk and for that thought-provoking summary, which I no doubt anticipate will stimulate a lot of conversation after during our dialogue session. Kapai, James. I will introduce our next speaker now, Dr. Emily Lane, who is Principal Scientist and Program Leader based at NIWA, based in Ōtautahi, Christchurch. Emily will be speaking to us on the tsunami and submarine debris flow generation in the near field. Emily, kia ora, over to you. Thank you very much.
Malolele, kia ora koutou, talofa lava. Thank you, Sean. And yeah, as he said, I'm going to be talking about the near field tsunami. And I'll try and be fairly fast about it, if I can get it to move forward. So yeah, this is the most significant volcanic tsunami in over a century. The last sort of this note would have been Krakatau in 1883. So that also sort of blasted the island of Krakatau away compared with what you saw. So this was sort of the before the big explosion, when you'd already had that flank collapse, and then after. And Krakatau caused a tsunami in Jakarta over 100 kilometers away that killed 36,000 people. So Tonga did really well to keep their deaths at 4. But there were still huge impacts. We've seen a lot of these. I'd just like to point out that this is a before and after photo that is 13 meters above sea level on the Kanakapolu Peninsula on this northwest part of Tongatapu. So, you know, there's huge impacts in Tonga. Volcanic tsunamis are actually really fascinating because unlike seismic tsunamis, where it's pretty much just the seafloor moves, there's lots of different mechanisms that can cause tsunamis from volcanoes. So you can get submarine or subaerial landslides. And so this is Anak Krakatau in December of 2018. An eruption caused this whole part to collapse away, so before and after, and this killed over 400 people. You've also got pyroclastic flows, so these supermobile mixtures of volcanic gas and ash and debris that can sort of flow down into the water and also generate tsunamis. There's also caldera collapse. So this is Tuhua Mare Island, just off the coast of the Bay of Plenty. So you can really see the caldera here. This is above water, obviously, but if this happens below water, then you know that change in the land surface can cause a tsunami. Also underwater explosions. You might have seen Yasion Shen's talk earlier today, and atmospheric pressure waves from the blast, and other people will be talking a little bit more about that in the far field. There's an underwater explosion in Myojin Shore. And just sort of looking at the Tonga-Hunga Ha-Apai bathymetry. So, I mean, these were the islands that you could see beforehand, but here's the caldera. You've sort of seen it before, and around that, it drops very steeply to sort of 1,500, 2,000 meters deep. And as James said, you can sort of see where past submarine landslides have already occurred. So this is, again, a slightly different timeline that sort of Cyprian Bossarel, one of my colleagues, has sort of put together as we're trying to sort of work out what's going on. But yeah, the eruption sort of started shortly after 4 a.m. UTC, so that's 5 p.m. Tongan or New Zealand time. There were a number of seismic signals. You got the big sort of sonic booms. But yeah, as Offa, I think it was said, that the first waves were actually observed in Kanakapolu before then. It was about 4:27 when there was the first wave in Nuku'alofa. There was also the cutting of the domestic cable and international cable, and the international cable was considerably afterwards. So trying to work out what's going on, we just sort of, for a timeline, we actually did a very simple thing where we looked at some cavities. So we're just sort of measuring, we're assuming that some of these events, and we're sort of assuming we've got multiple events happening, we're just modeling them as sort of these cavities. This could be an eruption sort of vaporizing that water. It could be a caldera collapse. But in this, we've also got a radiating atmospheric disturbance. And so with this atmospheric disturbance, again, Offa showed you this. This is what was measured in Nuku'alofa by the Bureau of Meteorology. So there's leading pressure trough of about 20 hectopascals. And these are, I've also showed these, but what I've done is I've stacked them according to the distance away from Tonga-Hunga Ha-Apai. And so you can sort of see the speed that this trough is traveling in this first sort of 300 kilometers, and it's actually traveling slower than the speed of sound, unlike in the far field. And this is at near Toputapu, and you can see here, this is the signal from the far field. And these are only 10-minute data, but if you sort of look at this 1-minute data and you average it to 10 minutes, you get very similar. So this is a model of Cyprian Bosserel's, and again, he's taking that atmospheric disturbance, and I think there's three sort of these cavities that occur. There was one there, and then you get a second one happening there, and I probably missed the third. But so this is sort of modeling. Now this doesn't capture it all because this doesn't get this inundation on this Kanakapolu Peninsula. So we're still sort of looking at what that might be. But if you look at the validation to the near field gauges, so black is observations, red is the model, and you can sort of see at Nuku'alofa, Vavau, and the NZG dart, you're beginning to capture sort of what we saw in terms of the waves. But one of the things that is missing in that model is that's just the shallow water equations. It's not a dispersive model. And Matthew Haywood did a lightning talk was yesterday explaining why this is necessary. And this is some modeling of his that he did on basilisk. And so you can sort of see the dispersive waves. So rather than just sort of a main wave coming up, you've got this wave train, and you can also see it sort of refracting around in the different speeds. It's deeper here, so it's going faster. It's shallower here, it's refracting around these different islands, but you sort of get this far sort of more intense wave train, and just sort of stopping it there. And this is a zoom in of this, but this is actually an image from the Sentinel-1, the Copernicus satellite program, where you can actually see those tsunami waves. And you can sort of see, if you look, you've got those three islands there, or those three islands there, and these ones here. So you can sort of see this dispersive pattern is actually what was seen on the day. So we haven't yet sort of put together, Cyprian and Matty are working together to sort of bring their models together. Another thing that James just talked about is this the cable breaks. And one of the really interesting things is sort of around here. So this bit here, which is approximately about here in this area, the international cable was actually dragged about 5 kilometers towards Tonga-Hunga Ha-Apai, which is here. And so this again, you've got the domestic cable here, you've got the international. I'm looking at a pyroclastic density current here, or the turbidity current from that. And so that's this red thing here. So this is a 2-layer model, but we're just looking at the pyroclastic density current. And you can see it flowing down the island. And it actually, you see just here, it's actually flowing back up. And so I'm sort of hypothesizing that that could be what caused this international cable to cut. And it didn't just happen like this, because the cable here was cut over an hour and a quarter before the international cable, but this is straight down from Tonga-Hunga Ha-Apai. So anything that comes down here, maybe a little flank collapse, could cut it. Whereas, you know, you need actually quite a big pyroclastic density current to make it over. There's a couple of saddles here and here that will stop smaller currents. So there's a lot of field work still going on, because there's a lot of things we don't know yet. So just a shout out to the Tongan tsunami team. So this is sort of Offa and his crew. I know they've been working really hard to get us information. Shane Cronin from Auckland University is also over there and has been working with them. James talked about sort of how he actually, Shane went over and sort of measured some of the depths. So you've got sort of over 280 meters deep there, which is considerably more than it was beforehand. And these are the islands that have been drastically reduced. The Tangaroa, the Niwa vessel, is also going out there to sort of look at bathymetry around the volcano and seafloor samples. So I'm really keen to hear about pyroclastic density current samples, because that's some of my work, and I want to see whether my hypothesis is correct about that international cable. But there's a lot of work going on. And yeah, we're only just beginning. Understanding the near field tsunami is going to be a detective story, piecing together lots of different strands of evidence. From the tsunami, there's those inundation extents on all the different islands, the number and the timing of the waves, if there's ashfall between it. And on Kanakapolu, we know that that one actually happened after an hour after the start of the volcano from an automatic weather station there. The sea level gauges, There's also the volcanic evidence, that the satellite images, timing, bathymetry changes, the seafloor sampling, and other evidence, cable breaks. And one of the really exciting things is the evidence from the tsunamis will actually tell us a lot about, you know, what might have happened in terms of the volcanics, but also, you know, the more we know about the volcanics, that'll help us refine our tsunamis. So thank you very much, Malo Pito, and I'll hand it back to you, Sean.
Loa Pito, Emily, thank you very much for that very interesting talk. And yes, we do hope your hypothesis. We are all looking forward to the Tangaroa and all of the good work that's happening on the ground. Ofa, Daniela, Shane, well done. Please keep it up. Thank you very much, Emily. All right, without further ado, I think we'll keep the water flowing. I will introduce now Professor Chari, who hails from the University of Western Australia, based in Perth. Chari, if you could kindly turn your camera on and unmute your speaker, and please take it away, mate. Over to you.
Okay, good morning here, good afternoon there. So I first would like to acknowledge that the first author listed here, Sarath Wijayaratne, did all the work, although I'm actually talking on his behalf. So locations, so the Tonga is in the red dot, and we'll be talking about whole of the Indian Ocean and Madagascar. So we're talking over 13,000 kilometers. It's about 11 hours at the speed of sound. Just look at the depths in the Indian Ocean. So the orangey color is basically of around about 6,000 meters. Okay, and we'll come back to that later. And we're going to talk about free and forced waves. So the free waves, what we have been talking about just now, that just like there is a disturbance and the waves basically propagate on their own energy. The forced wave is where you would actually have like a ship wave here, where the wave is actually dependent and linked to that. So most of what we're going to talk about today about a meteor tsunami is as a forced wave. So we already looked about this in terms of, so we're talking in this particular case as a volcanic and a meteorological tsunami. So a little bit of mathematics, we're talking about a meteor tsunami. So generation from a meteorological or an atmospheric disturbance, in this case, is a traveling pressure jump. And Proudman in 1929, a long time ago, basically presented this idea that you could actually have resonance if you have this Froude number was equal to 1. Maybe this one actually tells us, so if you have a pressure jump, so this is in the atmosphere traveling with a speed of v is equal to the shallow water wave speed, then we would have resonance. And this basically, as this moves, it works like a paddle, and this wave in front will start growing. That's this particular limiting case. When the Froude number is equal to 1, the disturbance increases with distance, but that's the idealized case. So I'm going to show you an example. This is from the Baltic Sea. Just want to show here, this is the wave speed. So this is the root GH. So out here, it's faster, and here it's lower. And now what we will see is a wave which is coming through. And then this is pushing, so high water level and low water level. This is our pressure jump. It's going past. But when it comes to deep water, what you will see is that the wave will detach itself from the pressure jump, and now it becomes a free wave. Okay. So this is a global event. Globally, these are where meteor tsunamis have been recorded and published, but we will put a lot more red dots in the Indian Ocean and globally. So this is the pressure jump. This is from University of Massachusetts. So you actually see the pressure jump moving across. So this is in the Pacific, but we're going to talk about in the Indian Ocean. Before I go, this pressure jump and the water level changes were found in the Mediterranean. Here is the pressure jump here in Sicily, and then in the Caribbean as well. So it was really that pressure jump from a global event. So I'm going to look at basically the Western Pacific and all of the Indian Ocean. There are 24 stations here. All of these 24 stations recorded the pressure jump and the tsunami waves associated with it. So here are some examples. So this is in Norfolk Island. You see a combination of seismic and pressure meteor tsunami. This is in Tasmania. Now going across to Esperance, you can see these fluctuations. And then Rodriguez in the Mauritius and Tuamasina in Mauritius. So right across the basin, we see the system. And now you actually see I've changed it. So 1 to 6, it's in here. So this is mainly close to the system. So this is what we talk about, the tsunami, the tide gauge was lost, but you see a lot more. This is mainly due to the tsunami waves. And as we go past, a combination of tsunami, seismic tsunami, and meteor tsunami, and then the others are meteor tsunami. I'll come back to those later. So we're talking about this Proudman resonance in here, and this is a picture by Hibia comments, and then what we're seeing is the seismic tsunami, what I'm going to talk about, and then the atmospheric signal in the system that we have resonance with the Proudman system. So now again, this is the Proudman, the shallow water speeds. So again, as we talked about, the orangey color is close to the speed of sound and the propagation speed of the system. So now we're looking at the speed of the pressure jump. So from Norfolk Island here across the Australian continent. This is from the Bureau of Meteorology. So you can see Norfolk Island, Brisbane, all the way through. So the propagation of the system, and it's the amplitude is decreasing, and also the wavelength is increasing as the system came across here. And if you take the mean speed, works out to be about 330 meters per second, close to the speed of sound. So now what we're going to do is to simulate this system by having only a pressure jump in an ocean model. This is ROMS. And then what you see is the pressure jump and then the water level change. So as the pressure jump moves across, you can see the forced wave. So the high water level is in red, and then you see that going all the way across the Indian Ocean into the African coastline. And that's really the meteor tsunami. So I'm showing you exactly the same here, except as still photos. So this is, remember, the forced wave. So it is moving the paddle, if you like, all the way. And once that pressure jump has moved, you actually have oscillations being set up across the whole of the Indian Ocean. So again, we go to this map, and now we're going to compare the observations in black, the meteor tsunami in red, and the volcanic tsunami signal in blue. So in Norfolk Island and Tasmania, you see a combination of both volcanic tsunami and the meteor tsunami. But when we come to Mauritius, you actually see only the meteor tsunami. And in all of these, in the far field, let's say in the Indian Ocean, you see the time of arrival here coincides very well with the speed of our simulations in the system. So now we can look at both together. So on top, we see the meteor tsunami due to the pressure jump, and then on the bottom is the seismic tsunami in the water. So very much dependent in terms of the Southwest Pacific, while the pressure jump is moving much faster and across the whole of the Indian Ocean. So just as the pressure jump comes, this is Western Australia, Hillary's is just north of Fremantle here, the pressure jump is actually moving away from the land, so you actually don't see any signal. And in here, when we go to Esperance, you actually see this change. Albany, you also see that system. But when we go and look at Fremantle and Bunbury, you see those waves, but except that they are 17 hours to 18 hours later than the passage of the pressure jump. And this is probably maybe due to reflected waves, through the system. It's not in all of the others, so those waves would have to be coming from the west, and also there was no local meteorological effects which makes it. So to summarize, we actually see the pressure jump, and then we see how the Proudman resonance and the passage of the pressure jump across the Indian Ocean caused tsunami waves across the whole of the Indian Ocean. Thank you.
Mahalo Pito Chari, thank you very much for that very interesting talk. And that really puts things into perspective of how unique and extraordinary this event was at a global scale. No doubt, I'm sure we'll circulate back to you during the dialogue and discussion. Kapai, thank you once again, Chari. I will now introduce our next speaker, Dr. Gareth Davies, who hails from Geoscience Australia and based in Melbourne. And Gareth will be talking to us on the tsunami effects in Australia. Thank you, Gareth, for being with us. Over to you, mate. If I can ask you to, oh, you've shared screen, and just unmute your mic. Thanks, Gareth.
G'day, everyone. Yeah, thanks very much, Sean. Thanks for the opportunity to speak here. So what I'm going to show today is a very early taste of work that's happening as part of a collaboration to release a data paper on the Tonga-Hunga tsunami observations, focusing on stuff in Australia, so especially Australian tide gauge and pressure data and other observations. So there's loads of groups involved in this, and I think it's really important that we can get out data to so that, you know, in future people can have a good record of what happened during this event and better understand these kinds of things. So part of this is the Bureau pressure gauge data, which locations depicted here. We've got over 400 stations, and basically for each of these, as is well known, you the Tonga-Hunga tsunami generated a land wave, so a horizontally propagating sound wave that caused big perturbations in the atmospheric pressure all around the world. So this is shown here at the top of a raw series near Pocos Island. And if you apply a high pass filter to these things to pull out, throw away all the long period components longer than about 3 hours, then we get the series at the bottom, which is like a residual. And so you can see here quite well, sorry, I'm just having some problems with there we go. You can see here quite well the land wave passing through in this record. And so it didn't just come by once, but it traveled around the world multiple times. What we can do then is we've got these kind of records at many, many stations, and so we can use it to study what the land wave is like. So this here is a plot of the, on the left here, the distance of each of these pressure gauges from the Tonga-Hunga tsunami, from the Tonga-Hunga volcano, compared with the time that it took for the pressure maxima to arrive, if we assume the pressure maxima left the volcano at 4:30 UTC. So in practice, what's happening near the volcano is more complex than that. But if you analyze it in that way, then you get, quite constant pressure speed in most cases. That's comparable to the speed of sound. A few gauges where it deviates from that, that's because of local weather effects where we're picking out the wrong pressure maxima. On the right side there, you can also see how the range of the pressure perturbation attenuated with distance from the Tonga-Hunga volcano. So we expect that in part just from geometric spreading, okay, like what happens for a tsunami as the wavefront size increases, but also because there's some sort of friction or attenuation of these kind of waves because they don't last forever. And so these sort of observations should help us better figure out how to represent that. In terms of the tide gauge data, here are the stations that we've got so far. You'll note that we've got data for all around Australia, but a particularly good concentration in the southeast, in southeast Queensland, New South Wales and Tasmania. And yeah, it's really a function of all the contributors who are contributing data to this, and this will all be released open source when we put together a data paper on this. So I'm going to talk now a bit about some of the interesting tide gauge observations that we have in Eastern Australia. Just before I go into it, I want to voice some caution about how we use tide gauges to observe tsunamis. So this plot here is showing two tide gauge records that are actually from the same site in Eastern Australia. They're 2 meters apart from each other on a jetty at the Gold Coast on the ocean side. And you can see that although they track each other quite well, there are clear differences in the high frequency content in the tsunami observations here. And that's because one of the gauges internally uses 1 minute averaging and the other uses 4 minute averaging. And so that often different decisions are made in tide gauges and that affect entire networks sometimes. And it's really important to understand how this is being done so that we interpret things correctly. But disclaimer, I haven't figured all that out yet. So I'm just analysing raw observations in what follows. So if we look at the tsunami size, then just focusing on the East Coast, on the right there, we've got a plot of the tidal residual range. So just strip out the long period components of the tide gauge and then look at the maxima minus the minima, gives you a measure of the tsunami size. And so what you can see is that in the sort of northern gauges that we have around central Queensland, it was relatively small, less than 0.5 metre. As you head south, the size starts ramping up around the border with Queensland and New South Wales. So sort of around the Gold Coast area, you start seeing places where you get over 1 metre of tsunami from top to bottom. And then that sort of persists throughout New South Wales, and we have some interesting observations, the largest one over 2 metres in the range at Crowdy Head, that we'll see in a moment. And then going further south into Tasmania, where it sort of reduces in size again, range in the order of 0.5 metre or getting close to 1 metre at some places. So with this sort of data, one thing we can do is use it to have a look at the relationship between the tsunami and the arrival of the pressure wave. So here's an example for Lord Howe Island, where the pressure wave arrived something like 2.5 hours after the eruption. And you can see that the tsunami sort of slowly starts cranking up after the pressure wave arrives. But in general, most of the action happens later. So here we had a tsunami maxima of about 60 centimetres above the sea level, around 6.5 hours after the eruption. At Crowdy Head, you see a similar story. Again, here the pressure wave is arriving around 3 hours after the eruption. The tsunami slowly starts rising over a few hours after that. And in this case, we get tsunami maxima around 1 metre in about 7 to 11 hours after the eruption. So this is kind of cool because, to my knowledge, it's possibly the largest actually measured tsunami on the east coast of Australia for which we have a tide gauge record. So I'm certainly not claiming it's the largest event to have happened because we haven't had Crowdy Head measurements or many other places for a lot of earlier events. But we saw in this waves of 1.8 metre peak to trough occurring repeatedly overnight with a 12-minute period. So that's like a full tide range in 12 minutes instead of 12 hours, okay? So the currents must have been hooking from this event. Really interesting. And at Crowdy Head, there are reports of associated with this substantial beach erosion happening overnight. Some surf lifesavers got in touch with us and said that was really surprising because the tide range wasn't large, so I think that's probably due to the tsunami. And also, even into the Sunday, the 16th, we saw regular surge events occurring, which were like a bit of a beach hazard for, if there's kids in the coast and it surges down, they go out and then they get washed off their feet by the incoming wave. So here is Port Kembla, and yeah, I just included this. This is one of those cases where the actual weather obscures our detection of the pressure front arrival. That's spuriously slow in this figure here. But you see a nice sort of late arrival at Port Kembla. So the 60 centimetres is quite prominent and occurring about 11.5 hours after the volcano.
Gareth, we are on 1 more minute.
Thank you.
Sorry for interrupting.
No, all over it. Yep. So I just want to show this record, which is really cool in Tasmania in the Huon River, which is a convergent estuary. And so what you can see here is from bottom to top, we're going sort of upstream in this estuary. And you can see the tsunami is relatively small in the coastal side, but beautifully amplifies as we go upstream. So this is data collected by Karen Palmer from UTAS, who's doing a PhD on this sort of stuff. And it's a really nice record here for further study. Social media also had various reports of interesting waves. The great movie from William Glamour on LinkedIn showing a wave of about 1 metre. Again, up in a convergent estuary in Middle Arm in Sydney Harbour, and other stuff on Twitter in Tasmania showing sort of inundation over relatively short periods. So yeah, summary is basically this event led to some marine hazards in Eastern Australia, most especially in New South Wales and Southeast Queensland. The biggest measured waves getting around 1 metres above what the sea level would have been. And quite consistently, we're seeing the tsunami maxima arriving a few hours after the initial land wave. So, we're thinking it's very clearly a role of both the meteor tsunami propagating from being amplified in the deeper waters, and also the effects of the volcano point source all contributing to this. So it'll be interesting to unravel that as we go on. And that's it from me. Thank you.
Mahalo Aupito. Thank you very much for that, Gareth, and very interesting talk. Yes, this event certainly set many instrumental observational records, and as you've clearly shown, on East Coast of Australia as well. We do look forward to that data paper coming out soon, mate. So good stuff. All right, last but not least, we always save the best for last. We do have Dr. Jose Barrero, who is director at Ecoast Consulting, who's also based in Whaingaroa Raglan in Waikato. And Jose will be talking to us about the tsunami effects in New Zealand. Jose, over to you, mate.
Kia ora, everyone. Thank you for letting me finish up the talk here. So I'm just going to talk a bit about some of the tsunami observations from the volcanic eruption down here in New Zealand. So we've seen a few of these animations. This is the wave coming across. This is animation done by Pat Lynette at USC with his students there. And the purple line was the radiation of the pressure front. You can see how it went ahead of the propagation of the water wave. On the right-hand side, we are showing the New Zealand based instrumentation. So we have the DART stations, which run up the Tonga-Kermadec Trench, as you can see. And we have the GeoNet tsunami gauge around the coast of New Zealand. I've also superimposed the track of Cyclone Cody, which was happening at the exact same time. And Cody's position when the volcano erupted was approximately here, about halfway between Tonga and New Zealand, and it was on its way to the south. And indeed, today I'm in Gisborne, and we are feeling the effects of another cyclone, which is following nearly the same track as Cody, interestingly enough. So we'll talk about some of these gauge observations. On the left here, I have your standard tsunami travel time plot. So this is square root GD, which is just the propagation speed of a shallow water wave. And on the right-hand side is the DART stations ordered roughly from north to south. And you can see the red dot on each of these is the shallow water arrival time predicted from tsunami travel time. But you also see that prior to that, you have the pressure wave happening. So in some of these stations, the pressure wave, or in all these stations, the pressure wave actually affected the water level first, and then you had the long wave coming later. And if we look at that animation-wise, this is another close-up animation from Pat Lynette's model. You can see that at the first part, the water wave was ahead of the pressure pulse, then the pressure pulse passes it, and you have the water wave coming after that. Also, as what Emily showed, you see this is done with the dispersive Boussinesq model, and you see the intense scattering and dispersion of the different wave trains. And as this wave comes into New Zealand, I want you to pay attention to it approaching the north coast. Here's Northland area. And there's a particularly intense patch of tsunami height predicted to come in right at the Whangarei Tutukaka area, which I will also discuss. And then we also see how the signal is rather long lasting. And in the interest of time, I will skip ahead. So here we have another plot of the, again, our gauges and measuring stations on the left. And now I'm plotting on the right the coastal observations at the GeoNet stations. So these are water level records that are recorded at a very high sampling rate. So we can see a lot more than just the tsunami long wave. We also can see even storm waves in these. These have been filtered here, but the red dot again is the arrival time of the long wave. And what we don't see as much happening before that arrival, and that's because the pressure wave is very small, the air pressure wave relative to the scale that we're at. This is a 1 meter spacing here. So we would only see a few centimeter little blip as in the plots that Gareth showed. And then the long wave coming in more noticeably after that. So some features, the first arrival in New Zealand was at Lawton Point, which is East Cape, the northern tip of the East Cape. And that is the sort of the preferential path of travel down the deep Tonga-Kermadec Trench. And that's why it gets there first. Then the largest signal on these stations was Great Barrier Island with a total wave height, so peak to trough of nearly 2 meters or over 2 meters, amplitude greater than 1. We see at Gisborne 2 strong surges, followed by a couple of hours of relative quiet, followed again by a resurgence of this oscillation of the Gisborne port. And then at Wellington and in Gisborne, a late surge, so a very late arrival at, not arrival, but a resurgence of energy in Wellington. This could be reflections or trapping of the wave energy off the East Chatham Rise, or you know, other effect or reflections coming from other parts of the Pacific. And finally, down in Poiseugur on the far southwest, we've got this very long signal that just persists and persists. And looking at the animations, you see the tsunami wave actually wrapping around all of Aotearoa and then meeting at the southwest corner. Tutukaka. So Tutukaka is in the north. Tutukaka is a known tsunami hotspot. It's been damaged by tsunamis in 2010, 1976, and in 2021, they were scared. My animation I'm showing here is a model I did for the 1976 event, but I just wanted to show the surges coming in and out of the marina area. You can see those pulses of high current speed jetting in. The height of the 1976 tsunami was about the same as March 5th, 2021, and it was about the same as what happened in this event, about a meter. Now, we have some video of what this looks like coming into Tutukaka Harbor. This was shared with us by Dylan Lease of the Tutukaka Marina. And this is the fuel jetty at the entrance to the marina. And that's what it looks like in real life. And here goes the fuel jetty snapping off and being pulled away. Now, this is what we would call moderate to minor damage in the marina. So imagine what severe damage looks like. We had one or two boats sunk, a few piles were displaced, and things like that. But it wasn't complete destruction, even to the level of what happened in Crescent City in 2001 from the 2011 from the Japan event. Stopping this is always hard. There we go. Okay, so looking at Tutukaka, here is the high frequency waves, or the high frequency data plotted as a spectrogram. And the green line is the event time. Sorry, the first red line is the event time. The green line is the shallow water wave arrival time. The red line is when the worst effects started to happen in Tutukaka. And I'm plotting here Lawton Point at the north. Oh, these are the wrong. Great Barrier, it should be North Cape and Great Barrier. Apologies for that. But what you can see is this dispersive curve here. This is the dispersion relationship for the propagation of water waves. And of course, the shorter period waves arrive later, and that's why you have this fall off. But this dispersive curve is quite evident in the data that we have. So we see that there were dispersive waves arriving in New Zealand. And you can see this dispersive curve on several of the stations, notably at North Cape on the left, Great Barrier, it's quite evident, and also at Lawton Point or East Cape. The places where you don't see it as clearly or at all, they're Gisborne, it's not there. Wellington, it's not there. And Poisiger down in the far southwest. So the dispersive waves really were filtered out in the northern part of the island. Also on these gauges, you see this band of energy up here. This is wind waves or storm waves. So these are coming off the cyclone, and we'll look more carefully into the timing of these arrivals. But the cyclone, as it came closer and moved down the coast, of course, pumped up the swell, and that's what we're seeing in these. So these are standard cyclone waves. So I think I'm on to my last slide. Yep, we are. Down in the Banks Peninsula on the South Island, there was also effects observed, interestingly, and some of these effects were of the scale of what was seen in the 2016 Kaikota earthquake and tsunami. So at Pigeon Bay, which is the eastern of these two arrows here, there was inundation in the campground, which we show here. And there was one family that was actually flooded and quite frightened and had their camping gear damaged. And then over in Port Levy to the west, there was large surges all day Sunday, and then through the evening on Sunday. There was fishing nets damaged and dragged around on Sunday evening. So teasing apart these signals, because at the same time we had the long wave energy from the cyclone coming in to the coast as well, and it was mixing with the tsunami energy and probably enhancing the resonances, because these bays are known to resonate on strong northeast swells. Others are working to compile more witness reports. Kate Clark and team at GNS has put together a series of surveys which have gone out, and that's also being compiled. So I would just say, in summary, there's still a lot of work to do. I'm not going to make summarizing points, and I want to acknowledge the people who contribute to the information that I shared, which are Alec Wild from NIWA, Dylan Lease from the Tuticaca Marina, Marion Scharnfeld from ECAN, Dougal Greer and Reese McIntosh at eCoast helped with the data plots and the spectrograms. Pat Lynette from USC, who did some modeling or has done great modeling and made great advances there. And then, of course, Emily, Sean, and Cyprian at NIWA, who we've been working closely for the last couple of months on this issue. So thank you very much. And I'll pass it back to Sean.
Mahalo, Pito, Jose, thank you very much for that very interesting talk, and very great to see. Thank you for all those details, in particular the dispersive ways and how they were filtered out in the North Island. That's all very interesting. I have to say, for the benefit of our audience, we have reached our final talk. So we do have time. Our event organizers, our kind technician Jess, has kindly advised that we do have about an extra 10 minutes up to about 3 p.m. New Zealand time, which enables folks to at least have a cup of coffee prior to the closing ceremony. Now, I do notice we don't have any questions in the live Q&A box. Not sure if that's a good sign or a bad sign, but I can say that there has been quite some very interesting discussion happening offline within the speakers dialogue. So I suppose I will open the floor to the panelists in case anyone would like to say anything. And if not, I'll perhaps kickstart with a question that Ha-Apai actually had directed towards the scientists on this call and other scientists who may be listening in, who can also contribute through the discussion forum, which is on there. So I open the floor. Daniela, Ha-Apai, Siautu, Sanna, Emily, Jose, James, Gareth, Chari, would any of you like to add any additional comments, given that we do have time and our audience hasn't asked any specific questions? So any generic comments or specific comments? Emily?
So yeah, I mean, there was a question from Ha-Apai about the that residual sea level change that sort of sounds like it was happening over the morning before the big eruption. And I mean, it's really interesting. It's sort of something that we do want to follow up with. I mean, the two obvious things are if there was some subsidence. And so, I mean, I don't know whether there's any GPS monitoring that happens on Tonga, but if it would be worth sort of comparing with that, if there is, because you could tell that. The other sort of obvious one would be looking at the pressure record, and again, if the atmospheric pressure was going down, that can cause the sea level to go up, and sort of the inverse barometer effect. And so comparing what you're seeing on the sea level gauge with those pressure records that we've got at Nuku'alofa would also be sort of useful to look at that. But yeah, I mean, it was an interesting observation, and yeah, we're sort of keen to work out what exactly was going on, but I'll pass it on to anyone else who might want to comment.
Jose, please take it away.
Yeah, well, I mean, it is an interesting signal. It happened over a span of multiple hours, it looked like, so almost a quarter of a tide cycle, and it was a scale of, I don't know, I think I looked at it quickly, but maybe 5 centimeters or so. So if it was air pressure, that I don't know if that fits what air pressure does, or I mean, maybe James can let us know. I mean, would it be possible that the whole, section of the crust was sort of deforming there by 5 centimeters, and possibly Tonga Tapu subsided for a few hours before it erupted? I don't know.
I don't know how it would do that. Doesn't mean it doesn't, but I don't know how it would.
Yeah.
Perhaps
Yes,
while we know that, oh, sorry, over to you, Ofa, please continue.
Yes, the increasing trend in the residuals happened before the Big Bang event. So the pressure drops only happened after the Big Bang. So these things I don't think are related to the air pressure changes.
I
Yeah,
don't
So
think
it makes a little.
it wouldn't be that big anomaly, but there was sort of some cyclical sort of like from memory from the pressure, there was sort of it was going up and down, maybe on the order of 3 or 4 hectopascals over sort of 5 or 6 hours sort of cycle. So it would be worth sort of just lining the two up and sort of calculating the inverse barometer. But Jose?
In tropical areas, if you look at air pressure plots from airports, I've looked at them in Fiji and everywhere, if you just look at it on a daily basis, it's high pressure in the morning, it gets lower through the day as it gets warmer, and then it gets higher. So that could have just been the natural diurnal pressure drop that happens atmospherically in an afternoon in the tropics, especially during cyclone season.
Yeah, I think it'd be good to have some further discussions on this. There was also a low pressure system around to the southwest. I don't know if that had any effects on that, but just to be sure that because my concern is us canceling the warnings on 11 o'clock in that morning. Our SOPs are wave amplitude related, and not the residual trend related. So I just want to make sure that it's a lesson that's learned, if something's to be learned for future reference.
Yeah, no, I think
Thank
it's definitely important to see whether we can learn from this. I mean, one of the things I'd like to say is that, I think those, the fact that there was that little tsunami the previous day, and all your work in actually sort of putting out those warnings, I think probably did save lives, even though you had cancelled them, because people were thinking about, volcanoes cause tsunamis, and so it was in people's consciousness, and I really think that that's part of why there were so few deaths in Tonga.
It
Thank you
truly
very
is a
much.
miracle that there was that few casualties, and there's the efforts that you guys did in warning your public, which are excellent. There was also the good fortune that it happened at 4 in the afternoon instead of 4 in the morning, And the good fortune that there were those precursor waves. Had the people at Hatafu not had a precursor wave, how would they have known to start getting out and then have the big one? So all in all, it is a miracle that there was only 4 people. I still don't believe it. It's just, hard to fathom.
Oh, most definitely. And thank you very much for that conversation. That's very interesting. But we do have a question for you, Jose, which has come through from Gail Arnaud.
Oh, no.
It's a simple one. What model did Pat Lynette use for the propagation that you had presented?
It's his model. It's the Cool Wave, Pat Lynette's own, and he runs it on a cluster of like 500 cores that he stores in a closet at USC. So it's his own private supercomputer that runs this it's not a very fast model, but it's pretty accurate and very accurate. And and he knows how to wrangle it.
Wow, just the words private and supercomputer in the same sentence. That's fascinating. We've only got 2 here in New Zealand. But
he built it himself, I think, too.
Oh, wow. Yeah, even more impressive.
Well, we've got the fastest one in the Southern Hemisphere in Perth. There we go.
Oh, there you go. But that was a very interesting conversation, because it's a question I've always had. This was a monumental event, especially in our lifetime. But when we look at just the scale of casualties compared to other, perhaps what I suppose in the tsunami world, what we would consider lower magnitude events, I thought it was just remarkable. So whatever factors were there, I totally agree with Emily and Jose that Ofa, Daniela, and the good work you guys did in the events leading up to the event, I think you well and truly did help save lives in that event. Mahalo lava, mahalo aupito. I suppose if I may, just to bring in our colleagues Siautu as well as Sanna, who I also see are are still on the call, and while we have the opportunity to ask some more social science questions. Susanna Siautu, how was the response from, because I understand you were also working directly with some of the affected farmers in country. Do you have any comments on how recovery has been going for the farming community or the primary sector in Tonga?
Oh, my Lord, Sean, I do apologize. Sana has had to go because as you all aware, in South Auckland, it's a little bit like Tonga and Samoa. We are still battling Omicron, and so while they deliver to Tonga, they also have a food hub here in South Auckland. So unfortunately, Sana hasn't able to stay on with us, but I understand from Emelina and the team that they have, from their perspective, they still have staff who are based in Tonga. And their crops for the coffee weren't affected, fortunately. So their coffee apparently has been able to withstand, and I think it may have been down to the way that they were planting, but Ofa is the expert. He'll be able to let you know whether the coffee's still grinding and whether it's still available there, the Tupuanga coffee. But just for me, I just wanted to say thank you all for your amazing passion, and malo opito Ofa Daniela, the miracle that it has been and the privilege that it has been for me as a social scientist to sit in and listen to your passion and trying to pull, as Emily said, pull all the evidence together and just try to understand this better for preparedness going forward. I guess from our space, we're working with Carol because living with the volcano now, I guess, is where the communities are heading towards. So what we're trying to understand and do is still try to break down some of that information offer for communities here and there. What we know about information is that no information is good information. To me, is wrong. No information is good information is not right at all. In the absence of information, we need to seek out good information to give to people in the interim while they're waiting, because there's a lot of emotions happening, especially for communities who are in the diaspora. So that's why for me, sitting in T-Surge, understanding what you guys do in the sciences, trying to get some bite-sized good information for the communities who are panicking is really, I think, the next phase for us in this disaster space, in terms of not just having silence, because silence is sort of where people start panicking and making things up, and then the coconut wireless can also turn against us and go a bit chaotic. So what we want to do is maximize the coconut wireless with good information. So the more we can connect with all of you guys to give us bite-sized information to give to the community, then the better the community can serve themselves. But that's it from me, really, Sean. I'm sorry to talk so long, but thank you everyone for your amazing passion and commitment.
Not at all, CO2. Thank you very much, Whaftai Lava, for sharing those very important thoughts. And in fact, it's a very, you hit the nail on the head there. And of course, Ofa, Tanyela, they would know. South Auckland and Auckland in general, you know, it's second home to a lot of Samoans and Tongans especially. So it was immense levels of anxiety across New Zealand, and no doubt in Australia as well. Families that were trying to call home, especially in those immediate days after the events. And you know, as hard scientists, we typically tend to focus on the science, you know, the physical aspect of the event. And we sometimes forget about the fundamental psychological aspects that disasters have for humans, you know, as a whole. So we do really appreciate your being here with us, Siautu, and also Sanna and Emeline. I guess, well, look, I suppose we do only have 9 more minutes until closing ceremony. So with your permission, everyone on this call, I will go ahead and bring this session to a close. I would just like to say a very big thank you once again to all of our speakers, Ngā mihi nui, malo au pito, and Whaftai te lava. Also, I would like to thank in particular our session organizers and our audience for your patience and participating in this session. I do acknowledge Jess, our technician, who has also helped ensure everything has run quite smoothly in this session. Now, from all of us here in Aotearoa, New Zealand, kia ora, and have a very long, have a great and long Easter weekend ahead. Cheers. Thank you.